Greetings and welcome back. So, in the previous vignette, what we did was to introduce what I would call the phenomenology of exploratory dynamics. The idea was, just as a reminder, that we have this 350 years of beautiful insights into what I will call dynamical systems, systems that evolve in time in a way that we describe mathematically using the so-called update rule. And that was great. And then I argued that there are a whole category of biological processes that are exploratory, where they go out, they come back, they go out, they come back, etc. And so now what we're going to do in this vignette is we're going to spend a few minutes trying to articulate how to describe the category of exploratory trajectories in a probabilistic fashion. So the way I would say this is that we've already spent a fair amount of time focusing on what I have referred to as the great probability distributions. And the argument that I made is that these great probability distributions are a quantitative way for us to express our null hypothesis. So a null hypothesis is, in our minds, we articulate a statement about how we think that the world is, and for some particular category of phenomena. And then we use mathematics as a way to sharpen that expectation, and it gives us an opportunity to go check things. So just to remind you, we've talked at length about diffusion. And one of the ways of thinking about diffusion, it's quite fun and interesting and deep. That on the one hand, I can think of diffusion as a coin flip problem, and on another hand, I can think of it as fixed law and PDEs, like the diffusion equation. But when we think about it as coin flips, we have our random walker who starts at the origin, flips a coin, can either end up at minus A or plus A, flips the coin again, and now can end up at minus 2A, at 0 or 2A, and so on. And there's a probability distribution that describes that behavior. And that probability distribution is the binomial distribution, which, just as a reminder, what I'm showing you here is essentially the statistical weights that correspond to the outcomes for different numbers of coin flips. So, for example, the first two little schematics refer to a single coin flip. There's two outcomes, H and T. One has probability P, the other has probability 1 minus P. Cool. The next one is I have two coin flips. So now there's basically three possible outcomes, which is heads, 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 tails, and tails, tails. There's a multiplicity of two for heads, tails, because I could do heads, then tails, or tails, then heads. Doesn't matter. So I can write the probabilities, and I have a whole distribution. So my argument was that these four distributions, the binomial, the Poisson, the Gaussian, and the exponential, will get us a huge amount of mileage. In other words, there's many, many problems, whether we're thinking about the waiting times for ion channels to open, the mean number of mRNAs for a constitutive promoter, whether we're thinking about the diffusion of behavior, the number of mutations in a genome. All of these kinds of questions can be cast in this sort of mathematical language. And what I'm going to put on offer now is the idea that when we want to think about exploratory trajectories, that we're going to invoke a new distribution, and now that distribution is the geometric distribution, which I will explain. So the geometric distribution is a useful way for characterizing some subset of exploratory trajectories, of some exploratory processes. And so let's think about this. So what I'm going to write here is a list of the trajectories, and maybe I will put that in quotes. And then over here, I will put the statistical weight. So we could succeed on the first step. So in that case, the probability is PS. But I might fail once and then succeed. So that has a probability 1 minus PS, that's the failure, times PS. So this is probability of success. I can next have the case where I have 2 failures. So maybe I should make a column called number of failures. So 0, 1, 2. The probability of this is 1 minus PS squared times PS. So the structure here is always the same. And what I mean by that is that the structure is fail, 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 I times, and succeed. The probability of a failure is 1 minus PS, where PS is the probability of success. So, I can just keep on playing this game. Fail, 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 succeed, dot, dot, dot. If I have I, then it's fail, 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 dot, 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 fail, S. There's I failures, and that has probability 1 minus PS to the I power times PS. So this is the so-called geometric distribution, for reasons that I think will become clear in a moment. So the geometric distribution is PI, which is the probability of I failures before a success, and this is equal to 1 minus PS to the I power times PS. Okay, great. So the first question that we might want to ask ourselves is, let's see here, I need to add a page. The first question we might want to ask ourselves is whether or not this distribution is normalized. So question. What is the sum over I equals 0 to infinity of PI, which is equal to sum I equals 0 to infinity of 1 minus PS to the I power times PS. I can take the PS out in front, so that's PS I equals 0 to infinity of 1 minus PS to the I power. And now this is the moment where we're supposed to recognize that this is a geometric series. So let's just take a little detour, a reminder. Consider the sum, Sn, as 1 plus x squared plus dot, 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 up to x sub n. That means that x times Sn is x plus x squared plus dot, 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 up to x to the n plus 1 power. And so if I take Sn minus xSn, so in other words, take the difference between these two things, what you find is 1 minus x to the n plus 1. Why? Because these things come in partnerships. So this x cancels that x. This x squared cancels that x squared. And that goes all the way down the line. There's an x to the n here, so that these two guys cancel each other. And I'm just left with these two terms. So given that, this implies that Sn is equal to 1 minus x to the n plus 1 over 1 minus x. And so, just adding another page, So this tells me as n gets larger and larger, if x is less than 1, I'm being a little bit sloppy and I'm not going to worry about it, then S infinity is equal to 1 over 1 minus x. So that's the sum of the geometric series. In other words, I'm making this claim, 1 plus x squared plus dot, 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 forever is 1 over 1 minus x for x. And there's a probably absolute value sign, and I'm not going to worry about that. Okay, so we've made our little detour. So now we're ready to come back to our question about the geometric distribution and its normalization, because what I have is this was equal to PS, sum I equals 0 to infinity of 1 minus PS to the I power. but this is PS, and then 1 over 1 minus PS. Why do I say that? Because 1 minus PS is our x, and so that is equal to 1. So, conclusion, our distribution is normalized. As we had hoped and as we had expected. So that was kind of our first exercise. Now what I want to do is I want to, given this philosophy of our trajectories characterized by failure, success, I now want to evaluate the average time we have to wait until we have a success. So next, the average time to wait until a success. And what I would say is that first thing we might want to do is let's calculate the average number of failures. So this is average number of failures. And I can write that as sum I equals 0 to infinity of I times pi, which is sum I equals 0 to infinity of I ps 1 minus ps to the I power. And I can always take the ps out in front. So that's ps I equals 0 to infinity of I 1 minus ps to the I power. And now let's use one of our favorite tricks. Define x is equal to 1 minus ps. And so this is ps sum I equals 0 to infinity of I x to the I power. And that's a form that we should recognize. The way I would put this is I've used this many times in the course, various courses, and in my online YouTube channel, Physical Biology, the Cell stuff. And the idea is that I can compute the moments of the distribution by taking derivatives. So I'm going to make a claim. This is the same as PS times x d by dx of sum I equals 0 to infinity of x to the I power. Why should that be? When I take the x derivative, let me highlight this. When I take the x derivative of this, what it's going to do is it's going to bring down a factor of I, and it's going to leave behind up here a factor of I minus 1. That's not the sum we want, but then when I multiply by this x over here, I promote that back up to the x to the I power, and so I'm left with the actual original sum that I wanted to evaluate. So that's great. So this is then equal to ps x d by dx of 1 over 1 minus x, because I know the sum of the geometric series. So now I can evaluate this derivative. I have ps x. The derivative of this is minus 1 over 1 minus x squared times the minus 1. And now I can go back and plug in what I meant by x. So this is ps 1 minus ps over 1 minus 1 minus ps whole thing squared, which is equal to 1 minus ps over ps. So that's the average number of failures. Let's say that the probability of success, just as an example, just to plug in some numbers and get a feeling for this thing, if p of success is 1/10, well, that means that the average number of failures is 1 minus 1/10 divided by 1/10, which is equal to 9/10 over 1/10, which is equal to 9. So on average, if the probability of success is 1/10, that means that we will have 9 failures and then we'll succeed on the 10th try. That's interesting because now we're poised to actually compute the waiting time, the time we need to wait. So if we assume this is a simplifying assumption, assume tau is the time step for success and failure alike, and I can later suppress that and have and will, then that tells me the average time that we have to wait is equal to tau times I plus tau. So this guy is the time of all the failures. And this, in this toy model, is the time of the success step. And we already said that this is tau. And now I can rewrite this as 1 minus ps over ps plus 1, which is the same as tau. And now I will get a common denominator, 1 minus ps plus ps over ps, which is tau over ps. Okay, that's the key thing that I wanted to do in this brief vignette, just to reiterate what the philosophy is here, at least my philosophy, which pretty much came up in the context of the pandemic, was that it was really fun and helpful for me to organize classes by making single idea bite-sized chunks. So this single idea bite-sized chunk had as its objective one thing, which is to say that for a class of these exploratory processes, it's a nice thing for us to mathematicize it using the language of the geometric distribution. What we did is we made a rational argument, a heuristic argument, maybe a scratch and sniff argument for how the geometric distribution arises. And then in light of that, mathematics, once we had that distribution, we did two things of interest. First, we confirmed that it's normalized by doing a little bit of math, a little bit of summing of series and things. And then we did something more interesting, which is we computed the average waiting time until a success. And that's something that we will come back to in the context of our next vignette, which is going to be about chromosome segregation. So just to put it in perspective, close out the perspective, what I want to do is talk about the exploratory dynamics as an alternative to conventional stuff of t now as stuff of t plus 4 plus before plus some correction, sort of Eulerian forward stepping, replacing that with models of exploratory dynamics. And we are finding our first entry into that to be the use of the geometric distribution. Look forward to continuing this next time.